This section is going to focus mainly on properties of polynomial functions and their graphs. Starting with definition 1, we are given that a turning point of a polynomial is a point where the polynomial changes from increasing to decreasing, or vice versa. In other words, a turning point of a polynomial is a local min or local max. So, with that definition, we take a look at these properties of graphs of polynomials, and we start off with let f of x be a polynomial of degree n, which means that that's the highest exponential power we have on a variable. The graph of f of x has the following properties. It is continuous and smooth, meaning we can trace the graph without having to pick up our pencil. It does not have any sharp corners to it. Point 2, it has at most n zeros, the degree power. It has at most n zeros, which could all be real, all complex, or some real and some complex. Complex zeros come in conjugate pairs, and real zeros are x-intercepts. And that's the main focus of section 2.2. So if you need a review on that, go watch those videos. It has at most n minus 1 turning points, which means that it has at most n minus 1 maxes and mins. Now the thing is, you may have a 5th degree polynomial and it only has 2 turning points, and that's okay. It's not a problem. The big thing to focus on in this sentence is the at most. So if you have a 5th degree polynomial, you have at most 4 turning points. If x equals k is a 0 of even multiplicity, then the graph of the polynomial would be tangent to the x-axis. So looking down here, this function, when it says tangent to the x-axis, it means it bounces off of it. So this one has an even multiplicity because it bounces off the x-axis. You could also say it does not change sign. The y values are all positive right here. Where it crosses the x-axis, it has an odd multiplicity. In this case, it goes from a positive y value to a negative y value. There's a turning point, and then we come up here from a negative y value to a positive y value. We have crossed the x-axis. That is a 0, and it has an odd multiplicity. In behavior is something we haven't really discussed a lot. The graph increases or decreases without bound as x approaches infinity. So to put that into perspective, this x-axis only goes between -4 and +4. That's all it goes through. So as we go this way, if we can imagine the x-axis continually going to infinity, positive infinity, then this end behavior, as we look at this graph out as x goes towards positive infinity, this end behavior increases without bound. So it means it's going to plus infinity in the y direction as well. Now if we take a look at the negative x-axis, if we imagine this negative x-axis extending out to negative infinity, this polynomial, as it goes towards negative infinity, the polynomial drops down without bound. So it goes to negative infinity without bound. Now, the thing is that if you remember from one of our earlier sections, we talked about flips, we've talked about reflections. So sometimes your polynomial can go to negative infinity, the x can go to negative infinity, but the polynomial is increasing without bound. So it's a matter of looking at the graph and looking at the coefficients and determining what's going to happen. This chart lets you see some things that could happen. The end behavior depends on the degree and the leading coefficient. So this is the leading coefficient. If the leading coefficient is positive and the polynomial has an even degree, it rises to the left and it rises to the right into a U shape. If the degree is odd, it falls to the left and rises to the right. So let's look at this one right here. It falls to the left, rises to the right, so it is an odd polynomial, and we can say that the leading coefficient is positive. Looking at the leading coefficient being negative, if it's negative and the function is, or the degree is even, then it looks like an upside down U, falls to the left and falls to the right. If it's an odd degree, then it rises to the left and falls to the right. So an example of that would be something like y equals a negative x cubed. It looks like this. So as we go to the left, and that's something about in behavior. We're talking about if you start in the middle of the graph, and if you go to the right towards positive infinity, what's it doing? If you go to the left towards negative infinity, what's the graph doing? So in this case, with the negative x cubed, it's rising to the left and it's falling to the right because it has a leading coefficient that's less than 0, that -1, and the degree is odd. Example 1 of this section asks us to use that chart from the previous page, which I've summarized here, to determine the end behavior of these three graphs. So taking a look at part A, we notice that n is odd. It's the highest exponential power. And we also notice that the leading coefficient, a sub n, is greater than 0. Right here, that 4, that's a sub n. So since n is odd and a sub n is positive, we're going to have the end behavior will do something like this. It'll fall to the left and rise to the right. So the function falls to the left and it rises to the right. Then if we take a look at part B, looking at the powers, make sure it's in descending order. Our degree is 6, so it's even. And our leading, our leading coefficient which is in front of our highest degree variable, is going to be 3, so it is positive. Since the function has an even degree and a positive leading coefficient, its end behavior is going to look like this. So going to the left, it rises, and going to the right, it rises. Let's take a look at C. On C, we have an odd degree, and we have a negative coefficient. Actually, the coefficient is just -2, and it's less than 0, so that's negative, which means that from our chart, if a sub n is negative and it's odd, the end behavior is going to do something like this. And I'm leaving this gap in here because the function can do many things between going to the left and going to the right in infinity. But just looking at the ends, ignoring what happens in the middle, all the zeros and those things, we're going to say when the degree is odd and the leading coefficient is negative, it's going to rise to the left and it's going to fall to the right. Example 2 gives us 6 graphs of functions that are not polynomials, and it wants us to go back to the first point on the properties of graphs of polynomials, which is up here. It says that a polynomial graph is continuous in one piece and it's smooth with no sharp points. So these 6 graphs on example 2, we are supposed to determine why these functions are not polynomials. On the first one, you note we have some sharp points, and also there's another property. It does not have an end behavior where it rises or falls to infinity. But I'm going to say sharp points as the main reasons for why it's not a polynomial function. On the next one, when we take a look at it, the end behavior is not correct. I'm just going to say bad end behavior. If it's a polynomial function, that last point under the properties said it's going to rise or fall without bound as x goes off to infinity. So this one is leading to a horizontal asymptote, it looks like, or at the very least it's going to oscillate up and down along that x-axis, so it doesn't have the end behavior that we're looking for. So on the third one, if we take a look at it, right here, we do have it falling without bound on the left, but it's approaching a vertical asymptote as it goes off to the left. You could also say off to the right, the function is not rising without bound. So I'm just going to say this is bad end behavior. Talking about that asymptote from before, I said over here on the left there's an asymptote. Let's talk about it a little bit more. If you have an asymptote, it's not continuous. So on this particular function, these vertical lines are representing vertical asymptotes for which the function does not graph. The function runs up very close to those asymptotes, but it does not touch them. So to get from this piece of the function to the other piece of the function, I have to skip over the vertical asymptote and come in from infinity. So it's not continuous, so it is not a polynomial function. On this one, we have an infinitely many zeros situation. You notice this function is going to continue to oscillate up and down. Even though its oscillations are getting further and further apart, it's still going to keep turning back towards the x-axis. So you could say the end behavior is not appropriate. So you could say bad end behavior. And we know it has bad end behavior, even though the end looks like, oh, it may be going to infinity. And this end over here on the left may look like it's going to negative infinity. But looking at the behavior of the graph, we know that these ends are actually going to turn. So it has bad end behavior because it has infinitely many zeros. So it's never going to go off to positive or negative infinity in the y direction. Likewise, this graph at the very end, it has horizontal asymptotes on either side. So because it has horizontal asymptotes, that means that the end behavior is not going to do what we expect it to do, where the graph goes to positive or negative infinity as x gets very large or very small.